Piecewise defined functions are functions that have individual pieces to them. It's not just one equation. It's two, sometimes three different equations that are put together kind of like a system, but it's considered one function. All right. So there are functions that have multiple parts. Okay. Each part has a domain that's given. Okay, so we're going to look at some piecewise defined functions and talk about how that individual domain for each part comes together to make the entire domain for the whole problem out of that. So that's what we're going to be working on, and then finding some function value and all those other things that we do with functions, we're going to do with piecewise defined functions. And the domain is actually referring to what? What's domain refer to? X values. Good job. So domain are their X values. The range is the what? It's the Y values. Okay, so we're going to talk about the domain and the range of some of these piecewise and actually draw the graphs for these piecewise functions, and hopefully, you know, kind of hang on to the good parts of this and be okay with it. All right, so let's look at an example of a piecewise defined function. F of x is equal to negative 3x plus 4, and then the other piece is x plus 5. All right, those are our pieces, and I usually put like a curly brace in there just so that it looks like I'm putting them together. And each piece is going to have a domain that's given for it. So like for this one, it might have a comma or a semicolon there, or they, you know, depending on, you know, what mood the book happens to be in, they could write if there, but I usually will just do a semicolon and then write the domain. X is less than or equal to -1. And then the second one has a domain for it. It picks up and says x is greater than -1. Okay. They do not always cover all of the x values. Like this one stopped at -1 and then the next one picked up at it. It doesn't have to do that. That's not a rule that it has to do that. Many of them do, but they don't have to. Okay. So when we look at this piecewise defined function, we see we've got a linear piece at the top. The first one is it's got a y-intercept of 4 and a slope of -3. The second piece is also linear. So we should have two straight lines or pieces of lines that we're going to graph when we go to do this. And then we're going to talk about the domain and the range of that. Now, in order to graph one of these, one of the things that you've got to find, or one thing that makes it easier, are to find the important points. The important points for a piecewise defined function are found using the x values that are listed in our domain. Okay, so this one has important points. The first piece has an important point at -1 for an x value. So what you've got to do is plug that in and find out, well, where is -3 times -1 plus 4? So that's going to give us -3 times -1 is +3 plus 4 is equal to 7. So there's an important point for the first piece at -1, 7. Okay, that's an important point. Okay. So when I go to graph that piece, let's go ahead and graph the first piece. And then we'll graph the second piece. All right. So I'm going to go to that important point that I found. -1, 7. So that would be -1 would be to the left 1 and then go up 7. 1, 2, 3, 4, 5, 6, 7. Yeah, that's right. So that point is there. I'm going to put a filled in dot there because the inequality has an equal to mark on it. If it doesn't have an equal to mark, then we're going to put an open circle. That's an important part of drawing these things. Now, what direction does this say the x values for the first half of this piecewise go? To the left. So that's toward what? The negatives, more negatives, right? So when I count my slope, that -3, then I'm going to count it to the left instead of to the right, because I normally would go down 3 and then right 1. But because my inequality says I'm going to go toward the negatives more, I'm going to count up 3 and left 1. And it's going to give me the same picture. And that will, then my line, when I draw that, is only going to go that direction. It's only going to go up and to the left. Okay? Because this is linear, I can do the slope counting. If it's anything else, I can also just plug in x values that are to the left of -1. So I could plug in -2 for x and work that out. -2 times -3 is -6, plus 4 is 10. And if I look at that ordered pair, that's -2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That dot right there is the same ordered pair. I can pick x values that fit this inequality here and plug them in to get points so I can get the picture of what it's doing. Okay. So now we've graphed the first half. Let's graph the second half by getting its important points. Well, the x value that's on that one is -1, right? So if the x value is -1, we got to find the y value that goes with that. All right, so to do that, we just plug in -1 into the equation. -1 plus 5 is 4, right? So that means I will go to the ordered pair, -1, 4. That's an important point for the second piece. Okay. Am I going to put a filled in dot or an open circle on this one? Why is it going to be open? Doesn't have an equal to mark on the inequality. So that's where I'm going to go to -1, +4, and I'm going to put an open circle right there. And it says that the x values of that are greater than -1. So what direction is that going to go? To the right, towards positives on that 0 and +1, +2. So I can follow the rule with the slope and go up and to the right, up 1 over 1, up 1 over 1, up 1 over 1. I could do that, or I could pick x values that are greater than -1 and plug them in to that piece to get points. That is the graph of our piecewise function. Okay. That's what this one's going to look like. Every one of them is going to be different, but that's what this one looks like. Now, with the graphing calculator, you can get it to kind of draw these. Okay, so the way to do that is go to your graphing calculator and hit the y equals menu. So you can put in an equation, and you're going to have to graph each piece as a separate equation. So the first piece is -3x plus 4. So I'm going to open up a set of parentheses and type in -3x plus 4. And then I'm going to close the parentheses. Then I'm going to open up another set. And this is where I'm going to put that domain at. So I'm going to hit x. And then I need the less than or equal to symbol. So to get that, I hit second math. And it comes up the test menu. And there's where my inequality symbols are. So the less than or equal to button second math, and then it's option number 6. And then I'm just going to type in the number, -1. And then I'm going to close my parentheses. Let's look at what it looks like when you graph that. See that little piece up there in the top? That's the piece. Now it draws this other stuff. What that's showing is, hey, you're not using any of these x's here. All of them go to the left there. It's not using any of those. So when I go to y equals and then go to y2 to get the second piece, I'll just do parentheses x plus 5, close the parentheses, open up another set, and then we want x's that are greater than -1. So x second math greater than is option 3, -1. And I hit graph from that. And there we have the other half of my picture there. And notice how it flatlined all the x values that are less than -1, saying that red piece is not using these. It's only using this other part. Okay.
You have to do one at a time.
You have to do one piece at a time. What you have to do, y1 should be your first piece. Y2 is going to be your second piece. If there's a third piece, it would be y3, and that you just keep going from there. All right, let's talk about the domain of this piecewise. The domain of that piecewise defined function. Well, we've got given domains for each piece, but we want the domain for the whole problem. Okay, so when we look at that, we see that it says the x values for the first piece are all of them that are less than -1 or equal to -1. So that means we start at -infinity and we go up to -1. Once we get to -1, we're using it for the first piece, and then we're jumping to the second piece. It starts at -1. So are we skipping any of the x values? I used -1 for the first one. I didn't use it for the second one, but I didn't skip any of them, right? So I went from -infinity up to -1, and then I stayed on -1 as the x value. I just happened to have a different y value, okay? And I moved over to the second piece, and it's all of the x's that are greater than -1. So that keeps going on up to positive infinity. So the domain for this piecewise is from -infinity up to positive infinity. It didn't skip any of the x values. Okay. The range. Range is one of those things that you could get the domain of a piecewise defined function without graphing it. So if they ask you just to find the domain, you don't even have to graph it to get the domain. The range, you can get the range without graphing it, but it's very hard. It's very difficult to do that. It's much easier to get the range when you have the graph drawn, because range, remember, is how far up and down the graph goes. Okay, so if we read this graph from bottom to top, what's the lowest y value that's marked there? That +4 that's right there, that -1, +4, that ordered pair right there. That's the lowest y value. So my range is going to start at 4. Am I including that 4 or not? And why am I including it or not including it? Look at that point that it's marked with. What's it special about an open circle? It's a parenthesis because we're not including it, right? Open circle means we're not using that particular spot. So it's a parenthesis. If it were a filled in dot, we would use a what? Bracket. Okay, bracket, remember, means this is part of the game. Parentheses means it's not. Okay, and then from there, this piece right here, it keeps going up, just keeps going up. But the red one does too, or the first one, the one on the left does too. So they both keep going up toward what? Infinity. So my range goes from 4 to infinity. One more thing that we'll talk about with this one, it's called continuity. on the range. Yes, ma'am. Continuity is the discussion of whether the graph is continuous or not. If something is continuous, just in everyday life, what does it mean? Never stops, keeps going, right? Okay. So on this one, if you're talking about continuity of a graph, it can't have any spots where you stop, right? So one of the ways that I always teach folks to look at continuity is try to trace the graph. Do you ever have to stop and pick up your pencil and move to another spot? Yes. If you do, it's discontinuous. Okay, so this one is discontinuous because we have to pick up our pencil. The range didn't have any skip spots in it, or the domain didn't have any skip spots in it, but our continuity, it's still be discontinuous because when we trace that graph, we got to pick it up and move to another spot. With a continuous graph, you would never have to pick your pencil up. Okay, continuous means it never stops, right? You never have to pick your pencil up. This one, if I try to trace that, I got to stop and jump down here to start over, to keep going on that graph. So it's discontinuous when you have to do that. So that's how you would determine if something is continuous or discontinuous. All right. Let's look at another graph. So we had g of x is equal to this particular negative 2x, x is less than negative 3, 3x minus 1 from negative 3 less than or equal to x less than or equal to 2. And then let's do one more piece. Let's do negative x squared for x's that are greater than 2. So this one has 3 pieces to it. It's got a good bit going on. I'm going to graph this, and then we're going to talk about the domain, the range, the continuity of this particular piecewise defined function. Okay, I'm drawing myself a coordinate plane. Now, anytime I'm going to graph a piecewise defined function, I've got to find those important points. Okay, so the first piece has an important point at what x value? Sorry about that, guys. Coming unplugged, man. What x value is important for the first piece? Look at the domain that's given over here. Negative 3. So negative 3 is an important point. Okay, we need to find the y value that goes with that. How do you find a y value given an x value? Replace it. So negative 2 times negative 3 would give me 6. So that's the important point for the first piece. So if that's the important point, I'm going to go to that spot on my graph. Negative 3, 1, 2, 3, 4, 5, 6. Am I going to put a filled-in dot or an open circle there? Why is it open and not filled in? That's right. Open is correct. It's not equal to. Equal to would fill in the dot. Because that doesn't have an equal to, we're going to have an open circle. That's exactly right. Okay. Now, I need to go in the correct direction when I draw the rest of that graph. So, which direction are my x values going? It says the x values are what to negative 3? Less than. So less than -3 would be going toward -4, -5, -6. Those are less than -3. So I'm going to go to the left, right? So I could pick some of those x values and plug them in. That works. So if I plugged in -4, I'd get +8. If I plugged in -5, I get +10. Or I could count the slope. Up 2, left 1. Yeah, up 2, left 1. That gets us the same thing. Okay. So there is the first piece of this piecewise defined function. All right.
Up 2, left.
Yep, up 2, left 1, because it's a -2 slope. Or I can pick x values that are to the left of -3 and plug them in. Both ways give us an idea of what the picture is going to look like. Okay. All right, now the next thing is to get the second piece. What's the second piece? How many important points do we think the second piece has? Look at the domain. How many x values are in that domain? There's 2 of them, right? We got -3 and +2. So it's going to have 2 important points. Okay? So I'm going to plug in -3 into the second piece. And I'm going to get the ordered pair. And I'm going to plug in 2 into the second piece and get the ordered pair. Okay? If I plug in -3, -3 times 3 is -9, -1 is -10. I'm going to go ahead and plug in the 2. 2 times 3 is 6, -1 is 5. Okay? Those are the 2 important points for that piece. So I'm going to go to -3, -10. 1, 2, 3, 4, 5, 8, 9, 10. I'm going to put a filled in dot there. Why did I put it filled in? Because it's got an equal to on the inequality symbol. I'm going to go to 2, 5. 2, 1, 2, 3, 4, 5. Filled in dot on it as well for the same reason. It's got an equal to on the inequality. What does the graph of 3x minus 1 look like? Is it curved or is it straight? Is it a straight line or is it a curved line? It's a straight line. It's slope-intercept form, right? We know that actually it crosses the y-axis at -1 because this y-intercept's -1. The slope is technically 3. So if I go up 3 over 1, I'll end up on that all those points there. So it's going to be this straight line connecting those 2 endpoints because the equation is a straight line, not necessarily because we're just connecting the 2 dots. You've got to have the idea of what the picture is, because you could have something that's curved in between there. Always, you have the option of plugging in x values that are between -3 and +2. You could plug in x values for x. In the 3x minus 1, I could plug in -2, -1, 0, 1 to get points on there. So if you don't know what it looks like, you can always pick x values that fit the inequality, and it'll work. You'll get the picture kind of started. Okay. Now, the last piece is -x squared, and it happens where x is greater than 2. So, important point for that one, that'd be at 2. 2 what? -4. Because when you square 2, you get 4, and then it's negative on top of that. So 2, negative 4. I'm going to go to that point. 2, negative 4. 1, 2, 3, 4. Is that going to be an open or a filled in? Open, because it doesn't have an equal to 1. What does the graph of an x squared look like? This in 100. Is it straight or curved? It's curved. It's a parabola. So normally x squared looks like that. Because it's negative, it flips down. All right. Now, how much does it curve? That's hard to tell. The best thing to do is just plug in some x values. What x values, because of the inequality, am I allowed to plug in? Anything but 2, above 2, or below 2? Above 2, right? So 3, 4, 5. I can pick any of those. I'm going to pick 3. 3 squared is 9, and then make it negative is negative 9. So if I go to positive 3, my y value is going to be negative 9. If I went to positive 4, my y value would be negative 16, right? It'd keep going down from there, but it's a curved line, something similar to that. I picture it in perfect. It's kind of hard to draw that parabola there without starting at the vertex. The curve, but it looks something like that. Now, from there, let's talk about the domain and the range of that. What about the domain? Looking at our inequalities up here and our graph, what do we know about the domain? Well, what this little red piece over here, which direction does it go? It keeps going to the left, doesn't it? So that would go toward what? Negative infinity. And then we get up to negative 3, and then we got to jump to what x value next? So we're get to negative 3 here, and that's an empty circle, so that means I got to move. And I move into the next x value here, which is negative 3. Oh, I didn't skip one. I used it again. And then I'm following from negative 3, and I keep going until I get here to positive 2 on the x values, and I got to jump ship again, right? And I'm jumping over here, but I used 2 there because it was filled in. I didn't use 2 here, but I've already used it up there, so I didn't skip anything. And then what does the green piece here do? Goes toward what? It slowly goes toward the right? And it's going toward positive infinity there. So this one happens to have a domain from negative infinity to positive infinity as well. All right, let's talk about the range of this one. Reading it from bottom to top. Let's go down here so we can see the bottom of that. What's this arrow here tell us? Keeps going down further and further and further. So let's start square. At the negative infinity. Negative infinity. Now we're reading at bottom to top. So we're going up. And it follow it to here. And notice, well, the blue one covers part of these y values, the same ones that the green one does, right? So they're counted twice. So that means we definitely aren't skipping any of those. What y value do I stop out with the blue one? Well, that's the x value. What's the y value that goes with 2 there? 5. So that's 5 as the y value. What's the y value that I pick up with on the red one? 6. Did I skip something?
Yes, you have to do that.
Right. So I'm going to 5, And then I'm counting 5 because it's a filled in dot right there, right? So I put a bracket on it because it's got a filled in circle. Then I'm going union. And what's the next y value that I pick up with? I'm going to go right after 6. And why am I putting a parentheses there instead of a bracket on the 6? Because it's an empty circle. Okay? These are the reason graphing it by hand is a little better than the calculator is because the calculator doesn't show you the empty circles or the filled in circles. You can't just glance at it and see. All right. So from 6, what does that piece up there at the top? Where does it go from there for the range? Keeps going up, right? So that's going toward infinity. There's the domain and the range. Continuity. Is this one continuous or discontinuous? Discontinuous. Discontinuous. Domain and range. Those are the main pieces when we talk about the graph of a piecewise defined function. Don't panic on piecewise defined function graphs. Think ordered pairs. That's what you want to think. If you'll every graph, and this is something that my high school students also struggle with, is they forget that every graph of any function that we deal with, no matter what kind, the basis of every graph are ordered pairs. So when in doubt, pick some x values that fit and get ordered pairs. You will inevitably end up at the right spot if you can plug those x values in and get y values that go back with them. Okay, so be mindful that always have the option of plugging in an x value. You just got to pick them that fit these inequalities. So I know if I don't know what the picture looks like, but I know all the x values have to be less than -3. I know I can pick -4, -5, something like that, and get some of the picture going. It may not be perfect. That's okay. It's going to get you in the right direction. I know that in the middle piece here, that the x values are between -3 and 2. So I know I just pick any x values that are between those two. -1, 0, 1. Those are between there. That gets me an idea of what that picture looks like. And then on the bottom one, I know that the x values, it says x is greater than 2. So I know my x values that I pick have to be bigger than 2. So I know I can pick numbers bigger than 2, 3, 4, 5, 6, any of those. All right. Now, that gets us an idea on the graphs. Let's look at some other things that we do with piecewise defined functions that are, I think, not quite as strenuous. Let's get a piecewise defined function, x cubed plus 2x squared minus 5 when x is less than -6. And then the second piece is 5x minus 8 if x is greater than or equal to -6. Okay. This is what we're going to do. We're going to find the function value. The first one we're going to find is f of +10. When they ask us to find a function value, what's the 10? Is it an x value or a y value? It's an x value. Look at your function notation. What's in the parentheses here? X. So that means this is an x, right? So now here's where the piecewise defined is different from all the functions that we did back in Math 100. The piecewise defined functions, you've got to decide which piece the 10 goes in because it only fits in one of them. Okay? So we look at the x value of the 10. Does 10, +10, fit when x is less than -6 or when x is greater than or equal to -6?
Greater than.
Why?
Because it's a higher number than the 6.
Yeah, 10, having $10 is better than owing somebody 6, right? So 10 is bigger than -6. So the 10 fits in this one. So that means we're going to use this piece. to find that function value. We're going to plug 10 into 5x minus 8. So that's going to be 5 times 10 minus 8. And we're just going to work that out. 50 minus 8, 42. Let's do another one. Same function, not changing it up, just looking at a different function value. They ask us to find f of negative 9. Where does negative 9 fit in the inequalities, the domains of each piece? Less than or equal, or less than negative 6, right? Negative, owing somebody $9 is worse than owing somebody $6. Okay? So we're going to take that negative 9 and we're going to plug it in to the first piece because negative 9 is less than negative 6. That's the reason we're going to use that piece. So we have to take negative 9 to the third power plus 2 times negative 9 squared minus 5. We're going to work that out. I'm going to use a calculator to help me out. So negative 9. Be careful when you're doing this that you put things in parentheses. Negative 9 cubed plus 2 parentheses negative 9 squared minus 5. So I'm just typing that in exactly like I wrote it. Negative 9 in parentheses cubed plus 2 parentheses negative 9 squared minus 5. Get negative 572. Good thing we're not graphing this. Same function. Let's get a weird one, or what seems to cause people problems sometimes. F of negative 6. Negative 6, where does it fit? Why the second one and not the first one? They both have negative 6 on the inequality. The second one has the equal to part. Okay? So the equal to part says, oh, it's on the second one, so that means that's the one we have to use to plug in negative 6. You know, guys, with the multiple choice Canvas quiz, when they ask you to do this and they have one of those, the answer choice, if you plugged that number into the wrong piece, is going to be on there. So you've got to plug it into the correct piece. So we're going to say 5 times negative 6 and then minus 8. And we'll work that out. So that'd be negative 30 minus 8, negative 38. So function value with piecewise defined functions, take your x value, compare it to the inequalities, find which piece to use. You're not going to ever plug it into all three of them. It's always just going to be one piece that you use for a function value, okay? One piece at a time. Piecewise defined function. That's the first section for the night. All right. Let's go to the next one. All right, next one is section 2.8. It's called function operations and compositions. Function operations means add, subtract, multiply, divide. Composition is a different game. Okay, composition of functions is a lot like function value, except for we don't have a number we're plugging in. We've actually got another function that has x's in it that we're going to plug in. Okay, so we'll get to the composition in just a little bit. We're going to deal with function operation and a few other preliminary things first. So let's, again, we're going to discuss domain. Remember in 100, we talked about domains of functions. What red flags, I think that's the name I gave them. exist for domain. There were two of them. Say that again. No. In an equation, what are the things that's what, if the x is repeated, were the things that made it a function. That's what you're talking about. If the x values are pieces of the domain repeated, that's what decided if something is a function. What we want to talk about is in an equation, what were the red flags that we looked for writing the domain of that function? Zero in the where? Perfect. Good job. X in the denominator. That x being in the denominator of the fraction introduced the idea of we could have zero in the denominator. If x is zero, then we got a problem because we never can divide by zero. So if there's an x in the denominator, that's a red flag. We got to do something about that. Does anybody remember the other red flag? Square roots in the problem. Okay? If we take the square root, what kind of numbers can we take the square root of and it not get messy? Or what kind of numbers cause a problem with square roots? The I, where did the I come from? Square root of what? Negatives. So when we're talking about domain with square roots, we're trying to find the x values that keep stuff positive or zero. All right, so remember, if there's an x in the denominator, we're going to set it equal to zero. If there's an x inside of a square root, we're going to set that stuff greater than or equal to zero. Those are the things that we did in 100. We're going to work on that a little bit as we're doing this. We're going to talk about domain of individual functions. We're going to talk about domain of our function after we do the operation or the composition on it. So we got to talk about those things. So let's look at a couple examples of just finding the domain, not doing any operation yet. Just find the domain. Example A, let's do f of x is equal to 8 minus 2x. So this one has the red flag of a square root. It's got an x inside of a square root. So if that's the case, we're going to take whatever's underneath the square root. It doesn't matter what's on the outside of the square root, as long as we're taking just what's on the inside. So we're going to take 8 minus 2x, and we're going to set that greater than or equal to 0 to find the domain of this function. Okay? So subtract 8. Negative 2x is greater than or equal to negative 8. One more step. Divide by negative 2. X is equal to, or not equal to, is less than or equal to 4. Okay.
Gotta change your sign.
Got to flip the symbol. Why did I flip that symbol around? What about divided by was negative. The negative 2 is the one that made the change. The negative 8, it makes the change on the sign, but it doesn't make the change on the symbol. The negative 2 on the symbol, what I divided by or multiplied by, changes that symbol. Okay, now how do I write the domain for x is less than or equal to 4? Well, if it's less than 4, that means it's going to get down there to negative infinity. It's going to get up to 4. There's the interval notation. There's the set notation. Either of those ways, be able to do both, honestly. has the bracket because it's got the equal to mark on it. X over x squared minus 9. What do I do? I set what equal to 0? The denominator. How do you solve that? Okay. Do what next? Keep going. Solve it. I'll be right back. All right, so we added 9 and got x squared is equal to 9, right? Now what? Take the square root. So that would be x is equal to just 3. Get plus or minus. Anytime you take a square root to solve something, you got to use that plus or minus. So that means those two x values are excluded because those would give us, if I plug in positive 3, 3 squared is 9, 9 minus 9 is 0, and that's division by 0. Okay, we can't do that. If I plug in negative 3 squared is still 9, 9 minus 9 is 0. So these two x values are excluded from that. So our domain is that. How do we write that in interval notation? We'll go from negative infinity up to negative 3. Skip it. Negative 3 up to positive 3. Skip it. And then 3 to infinity. Those are the way you could write the domain. Set notation is the top one. And then that's interval notation. Remember, if we had to skip a number, parentheses u, parentheses that number again. Kind of reviewing some of that stuff. Okay. All right. All right. I'm give you a second here. All right. So with function operations, it's just adding, subtracting, multiplying, or dividing. And they're going to tell you what to do. They're going to give you a couple of functions and ask you to do that. So let's take a couple of functions. F of x is x squared plus 5x minus 3. And g of x is negative 3x plus 4. Those are our two functions. Okay. The first example tells us to f plus g of x. So that tells me to add function f plus function g and get the answer. Combining like terms, simplifying any way that I can. Okay? So what that means is take f of x plus g of x. That's all that means. So f of x is x squared plus 5x minus 3. G of x is negative 3x plus 4. I'm putting them in parentheses there just so that we see this whole contains f of x, this thing contains g of x. The addition came from what they told me to do. Okay? The next thing to do is look to see if you got like terms that you can put together. Okay? So x squared, is there any like terms to x squared? No. So I'm going to just put it as part of my answer. 5x. 5x plus what? Negative 3x. What's 5 plus negative 3? 2x. Okay. Negative 3 plus 4? Positive 1. That is f plus g, bless you, of x. What is the domain of that function that we got at the end? Are there any red flags to that function? There's no square roots in there. There's there's not even a denominator to look at, right? So there's nothing, no red flags in there. If there are no red flags, the domain is what? Negative infinity to positive infinity, all real numbers. Okay. So that's function addition. Let's do subtraction. Okay, so f of x minus g of x. That's all we're doing here. Taking f of x and subtracting away all of g of x from it. So x squared plus 5x minus 3 minus negative 3x plus 4. The signs are going to change because you got a minus there. So x squared stays the same. 5x minus negative 3. That's a double negative, so that'd be positive 8x. Negative 3 minus positive 4. Negative 7. So f minus g of x is that. The domain of this one all real numbers again, right? No red flags to do anything with. That's why it's from negative infinity to positive infinity. So function subtraction there, the operation we're doing. Be careful about, the sign. That's why the parentheses are helpful. Is on subtraction, the parentheses really help a lot. All right. Let's get a different set of functions. Let's say we had f of x was 3x plus 5, and g of x, let's make it simple, x minus 7. And they want us to do f g of x. What operation are they asking us to do right there? Times. Multiplying. When they mash it together like that, it's multiplying. So we're taking f of x times g of x. 3x plus 5 times x minus 7. FOIL method, distributive property, whichever way you want to call that, that's all this is. So we're taking 3x and multiplying it to both of those pieces. And then we're taking 5 and multiplying it to both of those pieces. And combining any like terms that we might have. Okay. 3x times x would be 3x squared. 3x times negative 7 would be negative 21x. 5 times x is positive 5x. 5 times negative 7 is negative 35. Like terms, we got a couple of them in the middle there, so we can put those together. So that's 3x squared minus 16x minus 35. And that's f times g of x. Domain. Again, no red flags to speak of. So it's again all real numbers. Negative infinity, positive infinity. Because there were no red flags to deal with. Okay. Same two functions, f of x and g of x. Same ones. You don't have to rewrite them. I'm going to just copy them down here so we don't have to flip back and forth. And f over g of x. What operation does that indicate? Dividing. So that's all we're doing is dividing those two functions. So we're taking 3x plus 5 and dividing it by x minus 7. We would normally look to simplify that if at all possible, which would involve factoring and all that fun stuff. We haven't done much of that yet. Okay, that's one of the things that's a pillar in this particular half of the course. So main thing here is setting it up and finding the domain. Okay, why is this one not negative infinity to positive infinity? Yeah, and we got red flag there. You got an x in the denominator. Okay, so that tells us, okay, this may be what the function is, and there's nothing else I can do to that. But the domain, I've got to set x minus 7 equal to 0. And then I get positive 7. So my domain are all x's as long as x doesn't equal 7. And if I write that in interval notation, I'm going from negative infinity up to 7, skipping over the 7, and then moving on to positive infinity. The division is where you normally have a domain that you got to do something about, unless one of the original functions has a square root in it or something like that. So, for example, let's say we had two functions. H of x is the square root of 2x minus 1, and k of x is 8x minus 9. And they want us to find h plus k of x. So here's an addition problem with two functions that are quite different looking anyway. So I would just take 2x minus 1 in the square root plus 8x minus 9. There is nothing you can do to simplify that because this stuff here is locked inside the square root. So we can't combine any like terms here because this part has the square root on it. So this is the function. The domain, what part of that is the red flag for the domain? The 2x minus 1 is inside of a square root. So what do we do with it? Set it what to 0? Equal to or greater than or equal to? Greater than or equal to. It's a square root, so we got to have 0 or positive. So that's why we use greater than or equal to. So setting that in there, add 1, divide by 2. X is greater than or equal to 1/2. So our domain are all x's as long as it's greater than or equal to 1/2. in interval notation, bracket 1/2 to infinity. That's our domain. Yes, ma'am. That's exactly right. All right, let's get one more function operation. Let's use the same two functions as we did on example G. And let's do one of the special case things that happens. And that would be where you might have k divided by h of x. K divided by h puts 8x minus 9 on the top and the square root of 2x minus 1 on the bottom. So nothing you can do to simplify this. It's not going to get any better. But the domain is a little special on this one because what's happening here? You got a square root, so we know there's a red flag. But where's that square root with the x in it? It's in the denominator, right? It's in the bottom. So this is a double red flag, is what you would call that. Because not only does this have to be a positive, but it can't be 0 either. So when we set that up to find the domain, we're going to say 2x minus 1. Instead of saying greater than or equal to 0, we're just going to do greater than 0 because it's in the denominator. We drop the equal to because if it's in the denominator, the only number in the world we can't divide by is 0, right? So we drop the equal to when that square root's in the denominator. It's one of those special cases. It doesn't happen very often, but it does come up from time to time. So it's a special case. And then we just solve it from there the same way we did the previous problem. So equal to. X has got to be greater than 1/2 for this problem. So x such that x is greater than 1/2. That's the set version. Interval notation for this one, instead of a bracket for the 1/2, we're going to have a parenthesis 1/2 to infinity. Okay. Parenthesis instead of a bracket because we can't have this thing equaling 0. It's got to be positive because we can't have a 0 in the denominator. So that's one of those special case scenarios for this. Okay, so we've done function operations of addition, subtraction, multiplication, division, and we found the domain using those. The next thing to do in this section is that function composition. Depending on where you went to high school and how long ago it was, how much of this you've done. Some of you may have not done this before, and that's okay. It's not that bad. It just takes a little doing, all right? You may not remember it being called function composition. You may remember this symbol, though. The way you read that is F composed with G of X. What this means, F composed with G of X, it's like function value. You take the G of X function and replace X with it in the F of X function. Okay? So it's what it does is it takes the Y values from the G of X function and uses them as the X values for the F of X function. So it takes the range from one function and makes it the domain of another function. Not that having that, you don't have to have that definition memorized. The mechanics of it are what we're at. Okay? So we're taking one function and plugging it into another one. That's what function composition is taking one function and plugging it into another. All right. So let's take a couple of functions. Let's say we have f of x is equal to 2x minus 1, and g of x is equal to 4. Let's do something simple. 4x plus 3. Let's find, for example, I don't know what letter we're on. I. Example I. Let's find f composed with g of x and the domain. Okay. F composed with g of x. That means you take the g of x function and put it into the f of x function. Okay. In the place of x. So we're going to take this stuff and put it in here for x in that function. That's what we're doing. That's what function composition does. So that's going to be 2 parentheses 4x plus 3, close the parentheses, minus 1. Taking that g of x function and replacing x in the f of x function. That's what function composition does. Okay. Now, work it out. 2 times 4, 2 times 3. So that'd be 8x plus 6 minus 1. Which is 8x plus 5. F composed with g of x is 8x plus 5. Are there any red flags anywhere in that problem? No. So the domain is from negative infinity to positive infinity. Because there are no red flags anywhere. Nothing to worry about. So, big fancy thing. It's got that symbol. Looks like the word fog, but it's not. That's not an O. So, like when you see that, the O, if I were spelling fog, I'd put the O on the line. F composed of G. It's this little circle that's floating there, floating in between them. It looks like the word fog. So if you come up to me talk about fog and stuff, I'm like, I don't know what you're talking about. But you say F composed of G, I know what you're talking about. Okay, so F composed of G. Now let's do it the other direction. Let's take that and do G composed with F. Okay, so that means take the f of x function and put it into G. So instead of this direction, we're going to take this and put it into there. 2x minus 1 into the 4x plus 3. That's going to be 4 parentheses 2x minus 1 plus 3. It'll be 8x minus 4 plus 3. Composed with F. X. Again, no red flags, so our domain is from negative infinity to positive infinity. All right, let's throw some red flags in there so that we've got to deal with some other things. Because that's one of the things, the big thing in these sections here, the domain is some of the harder parts, getting the domain right. So we want to throw some examples out there at you that's going to help you with that. So what are we on? Okay. So let's say we have f of x Let's use the 2x minus 1 again, and I'm going to throw g of x to be 4 over x minus 1. And let's do a composition. Let's do f composed with g. That means we're taking g of x and putting it into f of x. Taking this fraction and putting it in the place of x in this function. That's all that means. So it's going to be 2 parentheses 4 over x minus 1. Minus 1. Technically, that's 2 over what? 1. Rules for multiplying fractions. Top times top, bottom times bottom. 2 times 4 is 8. 1 times x minus 1. X minus 1. 1 times x minus 1 be 1 times x is x. 1 times 1 is 1. This minus 1 is still there. There's our function composition. There is a little bit that you might can do, but it's not going to make it look any prettier than that. You could get a common denominator, you'd end up with one big fraction, but it's going to be a lot uglier than this is. Okay, so there's nothing really we can do to simplify that. The only thing that we can do is look at the domain. What red flag pops up here? X in the denominator, right? So that x minus 1, we've got to do what with that? Set it equal to 0, solve it. X can't be 1. So our domain starts at negative infinity, goes up to 1, skips it, and goes on to positive infinity. In set notation, that's a little easier for when it's x in the denominator, but interval notation is handy to know. Here we had an x in the denominator. All right. Do another one. Get a different couple of fractions or functions here. F of x, let's call it square root of x. And then g of x, let's do 3x plus 5. Matter? Let's see here, what letter are we on? L. L, let's do f composed with g of x. What does that mean do? Not multiplying. We're plugging in what? Which one goes into the other? 3x plus 5 goes into the square root of x. So this is going to be square root of 3x plus 5. That's what.
You have that square root.
Because f of x has the square root.
Oh.
So we're taking f composed with g means take this and put it in for x over there. That's what that means to do. Okay. Now, not anything I can do to simplify that. So there's my composition function or my composite function, which you might hear it called. But the domain. How do we find the domain of that? Set it what to 0? Greater than or equal to 0. Because it's under the square root, right? So solve that. Divide by 3. X is greater than or equal to negative 5/3. So set notation. Interval notation. What's our interval notation for that? Read the inequality. X is greater than or equal to negative 5/3. So the first number will be the negative 5/3. Bracket negative 5/3 up to positive infinity. Yeah, you did it the other way, right? Gotta be careful about it. Easy mistake to make. And I'm sure the other way would be as an answer choice. Almost positive. Okay?
Why did you put that? Bracket?
Because it's got a bracket because it's got an equal to mark. Parenthesis means it doesn't have an equal to mark. Bracket means it does. Okay. Same two functions. Let's do G composed with G of X. G composed with G of X. Remember, G of X is 3x plus 5. What does that mean we're doing? Plug G into itself. So we're taking 3x plus 5 and replacing the x on it with the same thing, 3x plus 5. Work that out. Three times 3x would be 9x. 3 times 5 is 15. You got plus 5. So it'd be 9x plus 20 is what it simplifies to be. What's the domain? Negative infinity to positive infinity, yeah. No red flags to speak of, so there's nothing to do about setting anything equal to 0 or greater than or equal to 0 or anything like that. There were no red flags.
So now the G composed of G, that's the function.
That's the composite function. Composite function is what that's called. All right, composite function is what this is called. All right, let's do one more. One more thing. Same idea though. So let's say we had two functions. Let's say we had f of x was 5x minus 7 and g of x was 3x plus 2. Something like that. And they ask us to find g composed with f of 3. G composed with f of 3. So to do this, it's a composition problem, but then they're giving us an x value. Okay, so we got to do the composite thing first, right? What's going into what? Is that right? Is it G into F or F into G? Look at the order. F composed with G means we take this one and go into that one. If you go the other direction, or look at another one, F composed with G means take this one and go into that one. Whatever's listed second is what's going into the other one, right? So G composed with F means take F and put it into G. All right, so I'm going to go ahead and just find the function, the composite function first. 3 times 5x minus 7. We're replacing x with g of x, or with f of x. We're replacing x with 5x minus 7. be 15x minus 21 plus 2. And then it asks us to find g of composed with f of 3. What does that mean do with the 3? Put 3 in place of x. So 15 times 3 minus 19. Which would be 26, right? Do your composite part first and then plug in the x value. Technically, you could have plugged in 3 into f of x, got that answer, and then plugged that into g of x, and got the same thing. But that seems like the kind of the end around the play or sexual duty play or something. Doing one thing and then you got to turn around and do something else. Yeah, it's just it's all the same direct. You know, you get to the same destination, you just go a different route. It works that way though. That you can take 3 and plug it into f. If I did that, 3 into 5x minus 7 would be 15 minus 7 is 8. And then 3 times 8 is 24 plus 2 is still 26. I get the same answer numerically, but I don't get this composite function if I needed to do something else. But do whichever way you want to. It doesn't matter to me when you're just finding function value. If it asks you about domain and things, you're going to need that composite function to look at out of that. So be careful of that. All right, so that's the second section. One more section to go. All right. Chapter 4. We're going to jump in out of chapter 2, jump over to chapter 4, not 4.4.4.1, and talk about inverse functions. Not every function has an inverse, right? Or it has an inverse function. Maybe the better way to say that, because you can actually find an inverse, but it may not be a function. So every function doesn't have an inverse function. 1-to-1 functions have inverse functions. 1-to-1 functions. So Teresa said something earlier about the not repeating the x values to make something a function. So that makes it a function. To make it a 1-to-1 function, you can't repeat x values. That gets you the function rule. 1-to-1 function says you can't repeat y values either. So it's 1x maps to 1y, and it only goes that 1x to that 1y. Okay? 1-to-1 functions pass a thing called the horizontal line test. So that's what we're going to utilize a lot to decide. Y'all remember us doing the vertical line test back last semester to test functions? The horizontal line test has the same rule. If it hits it more than once, it fails. Okay? Remember we did the vertical line test on, I'm just going to sketch a little graph here. Maybe you had something like this. that right there passes the vertical line test because I can drop a vertical line anywhere on there. It only touches it in one spot every time I drop it, no matter where I put it. Okay? This is a function. This is not a one-to-one function because when I drop a horizontal line on it, I can find several places where it hits it twice. So this is not one-to-one. I'm going to sketch another one here. Something simple. Straight line or a slanted line like that. That is a function because it passes the vertical line test. No matter where I put the vertical line on it, it only touches it one spot. Also passes the horizontal line test. No matter where I put a horizontal line, it only touches that graph, that blue line, in one spot. So this is an example of a one-to-one function. It's not the only kind of one-to-one function there is, but this one is one-to-one. So horizontal line test determines if a graph is a one-to-one function. Got to pass the vertical line test to be a function. Horizontal line test to be a one-to-one function. And remember, one-to-one means 1x to 1y. No repeating x's to be a function. No repeating y's to be a one-to-one function. I believe my wife and I are one-to-one. I was meant to be Matt to her. She was meant to be Matt to me. I don't think there was anybody else for me. Namely because nobody else would put up with me. But don't tell her that. Okay. Now, so one-to-one functions, we're going to test some functions to see if they're one-to-one. We're going to use the calculator to help us do that because it'll graph things really easily. So we're going to use that to help us keep us from having to draw a bunch of graphs by hand. Okay, so let's start with something easy. Is the function 1 to 1? Basically, it's another way of asking, does it pass the horizontal line test? So here's our function. F of x is negative 4x plus 7. So I would go to my graphing calculator. I would press the y equals button. I would delete anything else I had in there. And I would type in that function, negative 4x plus 7. And then I would hit graph. And I would test my vertical line test, and I would test my horizontal line test. Does this one pass?
Yes.
Both of those. So it is one-to-one. Passes the vertical line test and the horizontal line test. Example B, g of x, the square root of 25 minus x squared. I'd go to my calculator. I'd hit y equals, clear out that one. Square root 25 minus x squared. Graph. Does that pass the vertical line test? Does it pass the horizontal? Definitely not. There's a lot of places I could put a horizontal line and it touched twice, right? So this is not a one-to-one function. Doesn't mean it's not a function, just means it's not one-to-one. Okay. All right, now, one-to-one functions have inverse functions. Okay, and those inverse, any kind of inverse in mathematics swaps the domain and the range. Okay, inverses swap the domain and the range. That's a key thing there. So inverse functions swap the domain and range. Domain is x values, range is y values, right? Okay. Domain and range swap to be an inverse. Okay. X values and Y values swap places. One-to-one functions, the reason their inverses are functions because if I can not repeat X values and I can't repeat Y values, when I swap those two, it's still fair, there's still a function because it's not a repeating going on. Okay, so one-to-one functions are special because their inverses are functions, and that's where we kind of hang our hat for this section. All right, now, inverse functions compose to give X in either direction, and I'm going to show you what I mean. If f of x and g of x are inverses, then here's where we get a couple of composition statements. So the function composition that we just talked about is what I'm referring to. When I say compose, that's what I'm talking about. So f composed with g of x simplifies out to be x, and go the other direction. G composed with f of x simplifies out to be plain old x. Okay? That only happens if they're inverses of one another. No other time will that happen. If you get anything other than plain x when you do those compositions, they are not inverses of one another. Doesn't necessarily mean that the two functions aren't one-to-one on their own. Just means that they aren't each other's inverse. That's all that means, okay, if you get something besides plain x. So what we're going to do is decide if two functions happen to be inverses based on that test. And so example C, f of x is equal to 8x plus 5, and g of x is equal to x over 8 minus 5 over 8. Okay. Are f of x and g of x inverses or inverse functions? That's the question we have. Okay, so we want to prove that mathematically that they are or are not inverses. So to do that, we're going to do function composition in both directions. So f composed with g. That means we're taking which one and putting it into the other. Taking g, putting it into f. Okay? So that means we have 8 parentheses x over 8 minus 5 over 8. And then we still have the plus 5 there. So instead of x, here on the f of x function, I've got this stuff. Okay? And I'm going to simplify that. So the distributive property distributes 8 to both of those pieces. 8 times x over 8 would just be x. 8 times negative 5 over 8 would be negative 5. Then we combine like terms. What's negative 5 plus 5? 0. They cancel each other out. Hey, I got x. It worked in that direction. It should work in the other direction, but I need to verify it. Okay, so we're going to do g composed with f of x. Okay. So that means we're taking which one into the which one? F into g. So we're taking this stuff and putting it here. Okay, so we have 8x plus 5 over 8 minus 5 over 8. Well, this piece right here, I can split that up into 8x over 8 plus 5 over 8, right? Because that's common denominator idea. And what's 8x over 8? Not 0, 1. It's 1x. And I still have the minus 5/8 from the original. What's positive 5/8 and minus 5/8? 0. They cancel out. So I do get plain x. That verifies that they are inverses. F of x and g of x are inverses. That composition in both directions verifies that. If it works in one direction and not in the other direction, you've probably made an algebra mistake somewhere in one of the two. Okay? Because if it works from left to right, it should work from right to left if they are inverses. So be careful of that. So doing it in both directions can help. Now, so verifying inverses, check with composition. That's what you can do to verify that things are inverses. What do you do when you want to find an inverse? Like you were given a function, we determine if it's 1-to-1. If it is 1-to-1, we want us to find the inverse function of that. So how do you find an inverse? That's the next thing that we want to do for this section. So finding an inverse. Example D. I think it's easiest to show with an example. Start with something really simple, like 3x minus 7. Right? Here's our function. 3x minus 7, if I graph that, it's a line that has a slope of 3, so it looks something like that. And that passes the vertical line test and the horizontal line test. Okay, it works that. So we know that's a 1-to-1 function. So that allows us to find the inverse function. What, back from the first page of this section, what do inverses do? Inverses blank, blank, and blank. Swap the domain and range. Domain is x, range is y. Here's x. F of x is the same thing as what? It's the same thing as y. If you go back to the original, what early on in math, talking about functions, y and f of x are the exact same thing. Okay? A inverse swaps x and y, or swaps the domain and range. So the first step is x equals 3y minus 7. You literally swap x and y. Okay. Once you've swapped them, you try to get y by itself again. That's your job. That's to find the inverse. That's what you're going to do. So you're going to swap x and y. And then the next step is solve for y. Okay? So in order to solve for y, I'm going to add 7. So that's going to be x plus 7 is equal to 3y. I've almost got y by itself. What do I do next? Divide by 3. So 1/3 x plus 7 over 3 equals y. That is the inverse. The way we want to write that is using function notation. Function notation for the inverse looks like this. F with a little -1 exponent of x is equal to 1/3 x plus 7/3. The way you read that is F inverse of x is equal to 1/3 x plus 7/3. Okay? F inverse. It's a -1 exponent. It's really all it is, but you read it F inverse of x. That is the inverse function for our original problem. Don't try to find shortcuts. They end up in the briar patch. Okay? So don't try to find shortcuts for finding the inverse. Literally do that step by step. Swap x and y, then get y by itself again. Okay? Don't try to find shortcuts. We're going to do some more examples, but I just want to warn you, don't try to look for a shortcut as we're working these. You've got to just do the algebra to get y back by itself. Don't think, oh, well, they just flip this and put that under that. That doesn't always work, okay, depending on the problem that you're given. Okay. Example E. Same idea. We're going to take a function and find an inverse of it. So let's say we had h of x is equal to parentheses x minus 3 cubed. All right, so this has got a cubed on it. And it makes me nervous because I'm not sure that's even 1-to-1. So it may not have an inverse function. How do I decide if it even does? Graph it. So I'm going to go to y equals parentheses x minus 3. Close the parentheses, exponent of a 3. And then hit graph. Does that pass the vertical line test? Yes. Does it pass the horizontal line test? The only question would be right here in the middle. It looks like it gets pretty flat. I'm going to zoom into that spot and see what's happening. So I'm going to hit, on my calculator, I'm going to hit zoom. And I'm going to hit number 2 for zoom in. And I'm going to move my little cursor over there to that spot. So I hit, just move the right arrow key over there to where you get there. And then I hit enter. And what I notice here is, it looks like it's getting flat, but where it's not as flat as it once was. So as I keep zooming in, if I zoom in some more, if I hit zoom number 2 and I zoom in some more to that spot where it looks flat, I'm going to zoom in some more and look at that. Look, man, it's still got some space in between it here. If I zoom in a little bit more, I went the wrong direction. Zoom, I hit 3 instead of 2. Yeah. Zoom 2. There. As I keep zooming in there, it almost looks flat, but I'm going to promise you guys, it's not. It's not perfectly flat. There is a little bit of, just a tiny bit of angle there the whole time. Okay, so there is no flat spot amongst that. Okay, it goes increasing the entire way. Okay, so that is not a flat spot there. It may look like it, but as you zoom in, you saw that curve still getting in there some. It's there. Okay? The curve's bouncing, not back out. Kind of, not really. It doesn't bounce. It just cuts through. Yeah, it just comes through and just cuts through the x-axis at 3 and then keeps going up. Okay? It's like a little blip in there. All right? Now, so that tells me that this is a 1-to-1 function. And then I'm going to find the inverse of that. So I know that this is really y is equal to x minus 3 cubed. So we got to do a little bit of thinking here. Remember, inverses do what with x and y? Flip them. X equals y minus 3 to the third. Okay. Now, for that, it's got a cubed on it. If it had a squared on it, I would take the what? I'd take the square root. Since it has a cubed on it, I'm going to take the cube root. Cube root is just a square root symbol with the little 3 as the index there. So the cube root of x is equal to y minus 3. How do I get y by itself? Got one more step. Add 3. So the cube root of x plus 3 on the outside is equal to y. That is the inverse function. So we're going to write it in inverse notation. H inverse of x is equal to the cube root of x plus 3. I want to show you a neat thing that happens if I graph that inverse function. So I'm going to go to the calculator. I've hit zoom 6 to get back to the 10 by 10 window. So zoom 6 will always get you back to 10 by 10. And then I'm going to go to y equals, and in the second equation on y2, I'm going to hit that cube root. To get a cube root, you hit the math button and then number 4. The cube root of x, and I'm going to press the right arrow key to get out from under the cube root, plus 3. I'm going to hit graph. And then on y3, this is going to help me illustrate my point. I'm going to just put an X and hit graph. Look at these two graphs. This line and then this one. If I were to fold this picture along this line, this diagonal through here, wouldn't they match up?
Pretty close.
Really close. Let me square the thing up and it'll look better. What I did was hit zoom 5 to square the window so it's the resolution is the same in both directions. Now it looks really even closer to folding along this diagonal. They would match up. Inverses do that. They reflect across the y equals x line. So that might be something you want to write down. That inverses reflect across the y equals x line. Inverses reflect across the y equals x line. So there, not only can you do function composition to determine if two functions are inverses to one another. If you do that composition, you get just plain x. Guess what? When you do that graph, that x that I'm talking about reflecting across, that's that x you get when you do the composition. The same thing. That's how it ties all together. The graphs, you can graph each function on the same coordinate plane and see them reflecting across y equals x. Then you know that they're inverse functions as well. So there's two really good ways of checking that. Graphs are not always the best depending on the functions that you have. If they're two pretty wild functions that are really, really far apart, you won't be able to see the folding. These two, for this one, they're not very far apart. They're real close together. So it's not a really wild one. So it's easy to see that reflection across the y equals x line. So inverses reflect across that y equals x line. That is a handy thing to have. All right. Now let's look at a little different function. And again, we're going to find the inverse of this function and kind of step it up a little bit on this one. Here's our function. F of x is equal to 2x plus 3 over x minus 4. And then over here on the side, they tell us x does not equal 4. Why did they tell us that? What part of that graph makes them have to tell us that? The x is in the denominator. That 4 that they're saying x can't be 4, this is a domain that they're telling us. But because if x were 4, this thing doesn't even work at all. So they're having to tell us that because we got an x in the denominator. No. It doesn't affect how we're going to do anything, but they have to tell us that. So if we end up, when we find the inverse of this, if we end up with an x in the denominator, we got to tell about it. We got to do that domain piece for that. Okay, we have to do that if there are red flags in the beginning. We need to show those red flags at the end. Okay, so let's look at finding the inverse of this particular function. I'll go ahead and tell you this is a one-to-one function. If you wanted to graph it, you could hit, I'm going to go to y equals and clear out all this mess. To graph that, you have to put the top part in parentheses, 2x plus 3, close the parentheses, divided by parentheses, x minus 4. You can either do that or hit alpha and get a fraction, 2x plus 3, x minus 4. We should see the exact same graph come up twice here. Yeah, and it does. So here's the graph of that. It passes the horizontal line test. These two never meet here. This never meets here. So it passes both of those tests. It's a weird looking graph. We're going to learn about this kind of graph later on this semester. Okay, so we'll learn about this kind of function, but we can still find the inverse of it without knowing much else about it. Okay, now to find the inverse, what do? Swap the x and the y. So everywhere there's an x, we're going to put a y. So that's 2y plus 3 over y minus 4. So when we swap x and y, anywhere there's an x, you've got to put a y. The next thing to do is try to get y by itself. This one's a little more difficult because you've got y in the top and y in the bottom. So what we need to do is get rid of the y in the bottom. To get rid of that, what's the opposite of division? Try again. Multiplication. Y minus 4 is what we're going to multiply by. That will cancel this out down here. So we get the y out of the bottom. Because that's the biggest problem in this equation is the big fraction part. So we get rid of that. Well, that gets us 2y plus 3 on the right-hand side. On the left-hand side, we've got xy minus 4y, or 4x, excuse me. In order to get y by itself, what do I need to get together? So negative 4x and the 3, and then we need to get the y's on the same side, right? So we're going to subtract the 2y, we're going to move the 4x. So I'm going to add 4x and subtract 2y. So I can do all that in one step. All right, so that gives us 4x plus 3. And then on this side, we got xy minus 2y. Well, it's not quite as far as it can go. We can do a little more. Because we learned some stuff in 100. Starts with F and ends with actoring. Right? What could we... Oh, yeah, we did. Or I did anyway. I already did it. I got pretty good at it last semester. So, what does the left side have in common? Y's. So that would be like the greatest common factor on the left side is y, right? So I can factor out a y out of that left-hand side. So that's going to give me y parentheses x minus 2. Okay, so that's the trick to this one. Is that step right there is the trick. Okay, now what's going on between y and the x minus 2? What operation? Or times. The opposite of that is division. we want to get y by itself. So we want to leave it where it's at. So we want to divide by the part that ain't y, which would be the x minus 2, right? So if I divide by x minus 2, it cancels out right there. There's y by itself, 4x plus 3 divided by x minus 2. Is y by itself? We found the inverse then. The inverse function, f of x, or f inverse of x, excuse me, is 4x plus 3 over x minus 2. What do I need to tell them about x? That x cannot equal what? Is it negative 2? Positive 2, right? The domain of that inverse function has to tell, I have to tell them that x can't be positive 2 because that would mess up the whole problem. If x were positive 2. So that factoring is the trick. That's the tricky ones there. So there's one of those special cases of things that can happen. Let's do another one of those because that's one is probably not enough of that. It's kind of like bowls of Cocoa Puffs. One's not enough. Right? Just kidding. You may not like Cocoa Puffs. You might be a sinner and like Fruity Pebbles or something. I never liked Fruity Pebbles. I don't know.
That's too nutritious.
You're such an old man. All right, so we're going to find the inverse. What should they tell me about this problem? What should be out here that I hadn't written down yet? X can't be what? X cannot equal 5 because that would mess up the whole problem. Okay? For finding the inverse, we would need to swap x and y, right? X, 3y minus 8, y minus 5. Now what? Multiply by y minus 5 on both sides. Good job. These cancel over there. That gets us the y out of the denominator. That's what we're trying to do here. So it gives us 3y minus 8 and then xy minus 5x. You're getting close to the end, folks, I promise. Now what do we do? All right, so I'm going to add the 5x over here, get rid of it, and I'm going to subtract the 3y to get all our things with y together. And our things that are not y on the same side. So we have xy minus 3y, and we have 5x minus 8. It's okay if you wrote those in a different order. If you wrote negative 3y plus xy or negative 8 plus 5x, that's okay. Now, what does the left side have in common? Y's. So we take y out, get x minus 3, 5x minus 8 still in there. What do we divide by? Last step. That x minus 3 is what we divide by. Works out beautifully to get y by itself. So, I don't know what letter I call this. G of x. So, G inverse of x is 5x minus 8 over x minus 3. But x cannot be 3 because the denominator has the x minus 3 in it. That is the inverse function. So after you see it the second time, it doesn't seem quite as way over our head a little bit. The more you do with that, the better it's going to get. It doesn't. Not every problem's going to have to do that. By all means, this is just the toughest ones have that. All right. Let's look at one more example here. Let's say we have f of x is equal to the square root of x plus 5. And we know that because it's a square root function, there's a domain issue. That x's have to be greater than or equal to -5 because of that. I don't know what letter we're on. H. Okay. We want to find the inverse of that function. Okay. We want to find the inverse of that function. So swap x and y. The x equals the square root of y plus 5. Which seems innocent enough. What do we do now? Can't do that. Trying to get y by itself. So I got to get that out from under the square root symbol. How do I get it out from under the square root symbol? Square it. The opposite of a square root is squaring. So we're going to square both sides. So we're squaring the entire left side and the entire right side. This squared right here cancels out the square root. They cancel each other out. That's what happens there. When you square both sides, you get y plus 5 out of the square root. And on the left side, you've got x squared now. Okay? Next. Just subtract 5. It's pretty easy after we got rid of that square root. So x squared minus 5 is equal to y. That's our inverse function. So f inverse of x is equal to x squared minus 5. Are there any red flags for that one? No. Not a square root in there. No x in the denominator. So we're good. Okay. All right. On Canvas, you'll have a quiz that covers all three of these sections. In section 2.6, I think like 17 through 41. In section 2.8, so these are numbers out of the textbook. I think that's right. And then section 4.1 is 3 through 87. The odds, obviously, on these, as the answers are in the back of your textbook, so that you can check to see if you're doing those correctly. And that'll get you some practice to get you ready for that Canvas quiz. Next week's Martin Luther King Day, so we won't be having class. Campus is closed that day. So no class next week. We will meet again on the 28th, which is my dad and my oldest brother's birthday. Guess which one's over?
So the Canvas quiz isn't due until the 28th.
The Canvas quiz is not due until the 28th. So you get 2 opportunities just like we had before. Okay, so I would suggest don't wait all week this week before you do this, because you'll come into it and be like you never saw it before in your life. So make sure you at least do your first attempt this week, and that gives you all week next week to kind of figure it out of that. So remember, as you're doing those Canvas quizzes,